Okay, so for our second example of mean inference, we're going to do one about fish. So it's, a researcher tests 150 farm-raised salmon for organic contaminants. The researcher found that the mean concentration for carcinogenic insecticide Murex to be 0.0913 with a parts per million, with a standard deviation of 0.495 ppm. As a safety recommendation, the EPA recommended screening value for Murex is 0.08 parts per million. Are the farm salmon contaminated beyond the level permitted by the EPA? Right. So you have wild versus, farm-raised salmon. Create a 95% confidence interval. Carry out the hypothesis test to answer this question. Explain if there's an error and what it might be. Right. So basically, you want to be 0.8 or less. The question is basically, is it more than 0.08, right? Are we above the level? So where do you have food or water or whatever the case may be, that always test for certain levels of things. You want it to be lower than the level, obviously, not that level or more is the general idea. Okay, all right, so I'm going to go to this here. So the mean, they told us, was 0.0913. They told us that they had 150 samples. And they told us the standard deviation was 0.913. So we don't need to calculate it from data this time. Okay, so this will be t dot inverse 0.975 comma 150 minus 1. And why is that? Well, it's a 95% confidence interval, correct? All right, 95%, 0.95. Which means alpha, right, is 0.05 for the confidence interval, which means I have 0.025 on either side, 0.025 on either side, correct? So from here to here is 975 to get my t star, or alpha divided by 2, essentially, right? Okay, so my standard error is the standard deviation divided by the square root of the 150, right? Because this part of the formula is the standard error. And then the t times the standard error is the margin of error, right? So that whole part right there is the margin of error, right? So the confidence interval is the sample minus the margin of error, and the sample plus the margin of error, right? So this is parts per million and parts per million. Notice that, right, we're labeling these because they're nouns, they're means, right? Population mean. Versus back here when we did these ones, the confidence interval was just a proportion. We didn't need to actually label those. It's just a proportion. Okay, so we'll go back to our notes here, and we carried out the confidence interval. So essentially, we are 95% sure the true proportion, or true mean, is in here for the parts per million. Is it 0.9928? Oops, nope, I think I screwed up here. .976, 0.913. Oh, I screwed up. This is not correct. This was 0.0495. That's the reason why I didn't. Those were the same both times. Okay, so I go back to the problem. Yeah, 495. I'm sorry. So this was equal to. Okay, my apologies. Okay, so does that match up now? It does match up. Okay, so we got to do the hypothesis test now. So 0.08 is the government regulation. We want to be at or below that, correct? So therefore, if in fact I'm more than that, I have a problem, right? So if I'm more than that, I actually have a problem. Okay? All right, let's get this out of the way. All right, so step 2 is, can I do this? Okay, well, we'll take this value, paste it. Oh, I need to get step 2. Copy. Step 2. All right, so these things were given to us, which means the population of the sample means is 0.08. Standard deviation of the sample means is this, which we got in this spreadsheet. The samples are likely because obviously 150 is a lot less than 10% of the population, and the data does appear unimodal or normal, basically, which is the given graph that they gave to us, or I gave to you. Again, if it was given actual data, you could make the graph pretty simply in Excel to verify that. Okay, so step 3 is actually doing it. Okay, so step 3 is actually doing it. So let's actually do it now. So this will be t dot distribution. I'm sorry, what am I doing? I'm doing the actual t. So this is going to be the sample minus the population divided by the standard error. That's my t-stat. So I got 2.79. Okay, so I gotta do a little bit of funky math here, because the basic problem is now I'm over here. I'm doing a right-tailed test, and I have a positive t-stat, right? I have a positive t-stat. So if I do the distribution, it's going to give me this area. So I need to do 1 minus to get over to here, right? So this is 1 minus t dot distribution of that value, comma, the number of values minus 1 is degrees of freedom, comma, true. So I got that value there is our p-value, or the area, essentially. Okay, so what did we do? Right, we got our t-value, t-stat. This is, we'll call that t-stat, right? Did I call it t-stat in the previous one? I don't know. I probably should, huh? Yeah, it's t-stat. T-statistic. Okay. All right. So we got this here. So what does that mean? Step 4. So our p-value is what? Our p-value is 0.00292 dot dot dot, which equals the p-value, which is clearly less than this by quite a lot. So thus, we should reject the null hypothesis, right? So this means our sample mean that was given to us is significant and not likely to occur. There is enough evidence to reject the null hypothesis. It is likely that the amount of Murex is over the EPA limit, right? Because we rejected null hypothesis. So our confidence interval agrees with the hypothesis test because we rejected the null hypothesis, and the 0.08 ppm was not in the confidence interval, right? So we look back here, right? 0.08 is not in the confidence interval. It's just outside on the lower end, correct? This is clearly all of these values are higher than 0.08, right? That makes sense. So if there was an error, it was a type 1 error because we rejected the null hypothesis when it might be true. This is not likely because our p-value is very low, right? It's very low. So in comparison, probably not. Could it happen? Absolutely. Likely? Probably not. Okay, let's look at our comparisons here. So there we go. Confidence interval, right? The alpha for the confidence interval, if it's 95% confidence interval, is 0.05. Okay, which means 0.5% either way here. So t equals 0 is our sample, And then our confidence interval for these line t-values that we found are here, which is plus or minus that value essentially. So it's the same value down here, but it's only a single tail. And now we're going to put t-stat on here. And you notice t-stat is way over here, which means it actually made it into the shaded region, which is aligned by alpha. And now alpha is only half at this point, so the alpha of the confidence interval is 0.025, right? Not the same alpha. It's actually different because it's a one-tailed, right? The t0 is 0.08 parts per million, right? And therefore we align here, right? Because the 0.08 is not in here, right? It's over here somewhere, isn't it? 0.08 is over here somewhere. Not in the confidence interval. And the t-stat is in here, right? Which means we did find enough evidence to say it's not a usual sample, because usual samples would be in here essentially.